So title is how to code the cloud using weak dress code. Okay. So dress code, you know, यहाँ पे dress का, the form of dress is bit different, but anyway, you will see. This is how I designed the title actually. How to code the cloud using weak dress code. So actually, this is one of the work that we are doing. I mean, we have done actually some time back. So there I'll give you some idea and then I'll show you how graphs can be really useful when you want to store data on a distributed system, something like cloud. Okay. So very beautiful concept. And this is, by the way, done by two students like you, Anupam Agarwal and Deepak Yadav, BTech students. Okay. So it's all done by people like you. So youth students are energy, right? They can do anything. Anyway, so there is this quote in computers in IEEE Computer magazine sometime back. Men are from Mars, women are from Venus, and computers are from hell. That's what we say once they make an error, right? So basically, whenever you store data or transmit data, errors are bound to happen. Von Neumann has said once that whenever you are doing any kind of information processing, errors are bound to happen. Okay. And so how do we correct these errors? Okay. How do we control these errors? It's a very, very important thing. Okay. So for that, there is a thanks to Richard W. Hemming, who invented a technique, the coding theory, which is foundation to your whole ICT branch. By the way, suppose one sunny morning you woke up and Gmail is down. Is it a reality? You will probably suicide, right? This is the nice, basically, uh, reality of these days. So cloud computing. So this idea actually, just like this, there was an idea that just like we have a road, right, or rail network, these are the public utilities, right? So people thought that maybe once the internet was developed, people thought that we should also provide internet also as a public utility to everyone, free to everyone. And I think in US, if you visit in some states or some cities, at least it is free for everyone, Okay. So it should be provided as a public utility, right? In India, it is not the case yet, right? But maybe some of you can start this as a company. But so same thing about computing. This guy here from MIT, John McCarthy, 61, he sort of thought that computing should be also be delivered as a public utility. Okay. Like anybody who wants to compute, go and compute and come back. Something like that, right? That is how cloud computing started. It's a very, very interesting thing. And then when you do these things, so basically you require cloud data storage. This is the, when you do computing, obviously you require. So I think if you look at the history of computers, in the beginning, there was a lot of activities like, mainframes. You must have heard about mainframes, right? Mainframe machines were there and people are used to log in from remote location and do things or something like that. But that evolved finally in cloud. Then in between, there was an era of personal computers, right? People will have their own laptops, desktops, and so on, right? Like, thanks to Steve Jobs, who actually created this personal computer concept. And I think you must be knowing that there was a quote by TJ Watson at IBM Research that, okay, there might be a business for 5 computers. So we should start a business in computers. IBM was not working on computers early, right? So that's how they started, doing this personal computer business, right? And then IBM, because Bill Gates' mother was working at IBM, okay, so he got the contract. I mean, that is how what that, I mean, some influence basically, So basically, anyway, so this is a really interesting thing. So how do we provide reliability and security? This is something a challenge in cloud data storage. So cloud means, I remember some time back, if you ask some people, I think there was some famous lecture, somebody says that all our data is in cloud. And I think if you ask your parents, maybe, not everyone, but some of the parents will say that data agar cloud pe hai aur cloud chale gaye to kahan gaya data, right? So the common misconception, right, about the cloud, right? So the thing is that here cloud means a distributed set of computers, right? And then where the data is has to be stored, okay? So it should, I mean, the cloud should be reliable and secure and should provide unlimited service. Okay, so this is the requirement. Some of these cloud services, I mean, of course, this slide is a little bit old, but so like Amazon, now you use, right, Voila, Dropbox, P2P cloud data storage, Amazon Elastic Compute Cloud in 2006, Google Apps started in 2009, iCloud from Apple started in June 6 to 2011, and there was a commission to on the leadership opportunity in US deployment of the cloud in July 2011, right? So some of these services, but now it is very common. This is also a little bit old slide, but there are services. I mean, sometimes these services are down, right? For example, you see this is in 2009, Gmail outage, right? So why these things happens? So I think if you access your Gmail account, I think I'm not sure the current number, but sometime back it was like if you log into your Gmail, so Google used to in their file system. So each each file is decomposed into bunch of packets, and these packets are replicated certain number of times. I think it was 35 or something. They were used to replicate around different servers. Okay, and so if you want to get the data, you can actually get by connecting to certain specific nodes. I mean, in the network. Okay, this is how it was done. So if suppose that bunch of servers are down and so on and so forth, right? Something may happen, right? So then there will be error or there will be an outage. This is a picture of IBM Cloud Data Center, Auckland. And I think this is in South Korea. If you Google on, if you search on internet, you will find, I think, a lot of interesting, like Facebook has a very big data center for all these, data that you click every day, photograph, whatever you upload or YouTube videos and so on. Anyone can anyone estimate me what is the size of YouTube? Any idea? Anyone can find on by searching, or you ask your chat GPT, right? Your buddy. It will be tell me the exact. I think it will be very difficult for you to tell anything. Anyone knows the answer or something. If you can find in the public, let me know. What is the size of any idea? Any rough guess? Size of YouTube. Every minute, how many videos are uploaded? Where we are storing all this data, right? It's a very striking question, right? How to store this data? Very challenging question. By the way, so I think nowadays for data storage things, they require a huge amount of resources, electricity. So to reduce the electricity uses, they create these data centers in in some sort of islands and so on, where or maybe underground and so on. All those kind of things are done with, so that water is there in surroundings, so that temperature could be uh, lowered, right? So this is something very basic thing. It's very costly also. That's why I think some of you know that we are working on DNA storage technology, where you can store data on the DNA, which is uh, very easy, because I mean, which is ultimate storage density, because 1 gram of DNA can store 455 exabytes of data. By the way, I should say that the current size of the internet is around 700 exabyte. Exabyte is in the order of 10 raised to the power 18. Okay, so it's a huge density. So 1 kilogram of DNA can store entire uh, information that is ever produced on this planet. So 1 kilogram of information, 1 kilogram of DNA is sufficient to store that much data. So ultimate density, right? So these kind of technologies will provide. I mean, this will be the technology of next century, because all these current cloud business, there will be a problem anyway. But these cloud services are unreliable. Why? So here data is stored in a distributed fashion, distributed storage system, right? There are different points and where you store the data. So these are made from unreliable individual nodes. What could happen? Hard disk failure, right? That could be a possibility at some places. Network failure, right? Or pair churning, or malicious node might be an entry. So how do we provide solution as a engineer or as a mathematician? How will you provide a solution to this problem? These kind of problems are there. So then you use what is known as coding theory for cloud. So coding theory, as I mentioned to you, is a branch which provides algorithms for reducing errors in any kind of data storage or data communication. Okay. And when we say that you correct errors, so there is some certain trade-offs. You actually correct as many errors as possible with minimizing resources. Okay, you should not use too many resources. So, you know, always there is a challenge for engineers how to use less resources to correct as many errors as possible, right? In any scenario, right? In any kind of data storage, in any kind of data communication. Okay, and so for cloud also, coding theory is there for to support that. Okay. So I think coding theory started in Bell Labs in New Jersey. Here is the Richard W. Hemming. I think if some of you have not seen his lecture, you and your research, it is available on YouTube. His own lectures when he is teaching about coding and how he thought about these ideas. It's a very interesting thing. When so he used to actually give uh, calculations. He was solving certain differential equations. Okay. And then he was giving this to computers. I mean, at that point of time, those computers are, you know, these general purpose relay calculators kind of thing. He used to give them the calculations on weekend. Saturday, Sunday chutti hai. Then he comes on Monday. There is an error and machine stops. Then he asked this question by frustration. When a machine can detect an error, why it can't correct it? And then he thought of creating these error correcting codes, which are the basic algorithms for protecting the data when you are, you know, or whenever you're doing any computation. So coding theory is everywhere. And the key thing is that redundancy is very basic error correction thing. So suppose we are talking to each other, and if I say something and you are not able to listen, so you will say that kindly repeat. Okay. So repetition is a very crude form of error correction. The same technology is used in engineering. So now what we want, repetition should be there, but we want clever repetition. We don't want too much repetition, smart repetition, so that we can still do the as many errors as possible. I should be able to correct and also minimize the resources, use of resources, right? This is the challenge. So applications are satellite communication, space communication, data transmission, storage, audio, video, mobile, biology, chemistry, everything. So we are going to talk about a little bit of cloud computing. So how to construct codes? Codes basically it requires discrete mathematics, of course, algebra, beautiful algebra, I would say, right? So there is a statement also you see by this guy. An ounce of algebra is worth of a ton of verbal argument. लोग fight कर रहे हो तो एक ounce algebra is sufficient for them, right? फिर वो उनका मामला शांत हो जाएगा, right? So this is what interesting thing. And so depending upon the application, you choose the algorithm. So here is a Google file system, a very bit old picture, but at least to give you an idea. So there are app, there is a master server, there are chunk mappers, you know, and so basically files are divided into different chunk servers. They are distributed. File one, chunk one, okay, file one, chunk one here. So you redundantly distribute these packets on different servers. Okay, this is how the Google file system work. Okay, so now and also so everything is known by this master server. If it fails, then you are gone. So there are applications here also, shadow masters. ये fail हो गया तो दूसरे ने job ले लेगा अपना, right? So this is how the whole thing. So this is really engineering thing. How do we control, right, and provide reliability? But if we do like this, actually, so normally engineers don't think too much. They just okay, replicate kar lo data, kaam chalega, right? And then he starts replicating. But then when he starts using more and more resources, then think okay, there should be a clever way, and then they come up with a better idea. Now look at this picture. Suppose you have 2 MB file, okay, 2 MB file. So I am dividing into 2 packets, 1 MB and 1 MB, A and B, right? And suppose 4 nodes are there. I mean, 4 computers are there, right? Node 1, node 2, node 3, node 4. So what I can do, I have placed A in node 1 and also in node 2, and B I have placed in node 3 and node 4. Just replication, right? The way right now the most of these file system works. Okay. Now what happens if there is a failure? Suppose node 1 fails, I can get it from node 2 because I know that information is there in node 2, right? I can replicate this. But if both node 1 and node 2 fails, you are gone. then you cannot correct the errors, right? Okay. So this scheme tolerates one failure. It cannot correct two failures, and also, but it's very easy. The only thing it has to do is just copy the data from the, while correcting the data. Whereas in this eraser code, what happens? You see here you are using clever way. Node 1 stores data packet A, node B data packet B, and node 3 sum of those packets A plus B. Can we sum the packets? Yes, because they are elements of finite field, right? Your favorite friend, right? Right, field with 256 number of elements, those packets are there, okay? And then there is another one, node 4, which is A plus 2B. Like this I have done. Now what happens? This can tolerate two failures. You see the beauty now. 4 nodes only, but now you can tolerate two failures. But of course, this complexity is increased. Disk input output is increased, because what happens now if you want to correct, right? So suppose node 1 and node 2 fails. Suppose two nodes fails, and you want to get the data. So you can get node 3, A plus B, right, and maybe node 4, and then you try to solve, right, for A and B. Sort of you have to solve some sort of equation actually to get the data. So basically, here bandwidth is increased. You have to download 2 MB. There it was only 1 MB. So there are plus and minus in both the cases. So the question is there any more smart way? The answer is yes. And there your graph theory will be useful. So there I'll show you how graph theory can be used. Okay. So depending upon the applications, in some cases, I mean, this is a repair bandwidth versus the storage cost. So for internet or wireless communications, you require minimum bandwidth region. So basically what happens, now what we are going to do, data is there, we divide into chunks, encode the data and throw in the cloud in such a manner that you contact any k nodes in the system and you can reconstruct the file. Any k nodes in the system. So suppose there are n nodes, you contact any k nodes and you will be able to reconstruct the file. And if a node is failed, you contact any d nodes in the system and repair that node. That is a possibility. So mathematically, you have to design something like this, which is beautiful, right? Beautiful thing, right? And this is possible actually. So there are two kind of things. Like one is minimum storage. So of course, on each node, I want to minimize the amount of data that we store. When we repair the data node, basically when we repair the node, we want to minimize the bandwidth also. I should not download too much data. These are the two conflicting challenges to us. So then in 2007, Demarcus actually came up with this idea of regenerating codes. Okay. So basically there are n nodes, data collector is there. Each can have alpha packets actually, Each node stores alpha packets or alpha symbols. So data can be collected by contacting any k nodes in the system. You contact any k nodes in the system. This is a very good idea. And when the node fails, there are two kind of repair mechanism. Number one is functional repair. What do you mean by functional repair? If a node fails, this property that I mentioned to you, that you contact any k nodes, you can reconstruct the file, will remain true. If that node fails, I replace it with some other functional data so that you contact any k nodes and still you will be able to recover the file. Okay, this is functional repair. And then there is what is known as exact repair. Whatever is lost, we want exactly that data at that point, right? So two kind of schemes are there, okay, for correcting errors. So by the way, this is about FQ. What is FQ? Field with Q number of elements, your friend, right? From day one. So here is the thing, data reconstruction. You contact any k nodes in the system and reconstruct the file, right? If one node is fails, you contact say d nodes in the system, and so the repair bandwidth is d times beta, and download beta packets from each. So repair bandwidth is D times beta, right? And you can repair. This is the functional architecture of the cloud, right? So data is not stored on one node, but on distributed nodes. Okay. So this is a multi-dimensional optimization problem. We want reliability. We want to correct as many errors as possible, basically as many node failures as possible. We want to minimize the storage. We want to store as less number of packets on each node as possible. Third, we want to minimize the bandwidth. We should be able to download only very few packets to repair the node. That's third problem. Disk input output should be also be just we should copy. We should not do any calculation. And scalability. आज हमारे पास 100 nodes हैं, कल हमारे पास 1000 nodes हो जाए, algorithm should work, right? So what could be the best algorithm? Any idea from you young people? You are the future engineers or competitive programmers only? हाँ? Competitive programming शुरू कर दिए? Okay. So if you can think beyond competitive programming, then only you can find a solution. So the question is, can we have exact repair with minimum repair bandwidth, minimum discrete and computations? We will use dress code. The dress code was invented by Kannan Ramchandran. Okay. So dress code means distributed replication based exact simple storage. Right. So नाम अच्छा देना है, right? So what you suppose you have data file को हमने 14 packets में divide किया. Okay. Then what you do? I add another packet 15, which is sum of all these previous packets, which is 15th packet. So I got x1, x2, x14 is transformed to y1, y2, y15. And these are our nodes, 6 nodes. And I am doing the replication like this, you see. So packet 1 is in node 1, node 2. Packet 2 is in node 2, node 3, and so on. This is a smart replication. The question is, how do you get this solution? Right? ये किसी ने बता दिया, चैट जीपीटी ने बता दिया, चैट जीपीटी बता पाएगा? I don't know, you can try. So basically what I'm saying that this is known as fractional repetition code. Basically we are distributing the fraction of data on distributed nodes, right? In a different manner, right? So in a smart way of replication. So packet 1 is replicated twice, packet 2 is replicated twice, packet 3 is replicated twice, and so on and so forth. So how it works actually, first of all. Let us take an example here. By the way, this example is, you already know. I think some time back I asked you this question. There are 7 points, 7 lines, and on each line there are 3 points. Through each point 3 lines are passing, right? You remember that? That is what is going to help here actually. See the beauty. How? You see. So we have 1 minute. ये क्या आ गया? So we have, suppose we have 6 packets. Suppose one file is divided into 6 packets, right? 1 MB each. Then we use a code. 7th packet is parity sum, just sum of all 6 packets, right? And then I'm distributing this on 7 nodes like this: 1, 2, 3, 3, 4, 5, 1, 5, 6, 1, 4, 7. How we are getting, I will tell you later. But first you understand, now it is going to do the job for you. How? So suppose some node fails. So basically, first of all, if you want to reconstruct the file, these all 6 packets, user can connect any 3 nodes in the system. You connect any 3 nodes and you will get 6 different packets. And because of the relationship, 7th packet is sum of 6 packets, you can get the 7th packet also, right? So you get 6 different packets by connecting any 3 nodes. You can see the beauty. This is the beauty, right? You connect any 3 nodes in the system, right? So this is something really interesting thing. That is first thing. Second, so I mean here, for example, if you look at node 2 will give you 3, 4, 5, 1, 5, 6, 1, 4, 7, right? What is missing? 2, right? Which is sum of all the other one, right? So you can get the value of 2, whatever it is, right? So this property is maintained all across 7 nodes. This is the beautiful solution, right? And another thing here, every packet is repeated 3 times. Replication factor is 3. Every packet is repeated 3 times. 1 is there, right? 2 is there, right? In 7, right? Every packet is repeated 3 times, right? Now you see, suppose node 1 fails. So you're gone with 1, 2, 3, packet number 1, packet number 2, and packet number 3. Now you contact any of these node, right? Suppose from here you can get packet 1, from here you can get packet 2, and from here you can get packet 3. So you can reconstruct the whole thing, right? Right. So what it does actually, it maintains a table. Which packet is at where? Based on that, you just extract, right? This is the solution. So this table-based repair, it requires minimum repair bandwidth because you'd only download whatever is required. Minimum disk input output calls or no processing of data. You are not actually in the previous one you stored linear combination of packets a plus b, a plus 2b. That kind of thing is not there, right? Straightforward data download. So this can tolerate any 2 node failures. Okay, 2 simultaneously node failures because replication factor is 3. So you can tolerate 2 node failures. But if 3 node failures will happen, it's lost. You're gone. Okay. So the question is, first of all, this kind of solution is there. It's a very beautiful solution. 2007 when it came, people said, wow. I also looked at it. Then we also said, okay, we should use some graph theory here. And I'll show you how we have used graph theory. Okay. So the question is, how do we get this solution? By the way, if we just replicate 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 4, 5, like this, it's not going to work. You want a smart replication, right? This user gets only 3 MB data if you suppose connect 3 nodes. So that beautiful property is lost, okay, if you do this. Now you see this guy is sitting there. You remember this? 7.7 lines, right? That thing. 7.7 lines. On each line, there are 3 points. Through each point, 3 lines are passing. Obviously, lines means only collection of points because this is discrete business, right? So that what? So you see, it looks like a curved thing, but it is just collection of points, right? Okay. So this is known as Fano plane, projective plane of order 2. By the way, there are many open problems. So first time projective plane of order 10 is not possible was done by a computer search. Okay. And a lot of interesting things are there actually. They are very quite useful objects. By the way, he is serving you better. If you take points here as packets and lines as a storage nodes, you get the same configuration that was there in the solution. So many times doing this beautiful discrete math things can solve some engineering problems, right? That is the beauty of discrete math, right? I wanted to show you, right? So basically simple idea, right? 7.7 lines, that idea configuration is actually solving your problem. So in general, we have some results here. And this is further generalized to what is known as standard triple system. So if you don't know about it, it's okay. You can read on your own. So question was open problem, whether we can construct dress codes beyond these 2 systems. Okay, and the answer is yes. So these people actually use graph theory, Salim and Kannan Ramchandran. So they used. Can you identify what is this graph? What is the name of this graph? It's a regular graph. Regular graph पढ़ाया गया है ना? या नहीं पढ़ाया गया? पढ़ा है, ठीक है. Regular graph की क्या property है? हाँ? What is the degree of V6? 5. V1, V2, V3, हर एक की degree same है, right? So regular graph, okay? So now this kind of regular graph you take and take vertices as node and edges as packet, you get a solution here. See another beauty. This time I have not taken Fano plane, but graph, a regular graph, and we have found a solution. Right. This is the beautiful application of graphs. Right. So here the replication factor is how much? 2. Every packet is repeated 2 times. Okay. So then there is a whole what you call fractional repetition code is a replication degree rho is a collection of n subsets of a set having theta packets, each having size d, right? Each UI can store d packets, right? Such that theta times rho is equal to n into d. This is a condition. I mean, formal mathematical thing, not required if you want to not to understand it. By the way, now you see, just by using this business here, this is our construction. Take two positive integers and form this set t raised for I plus 1 plus j modulo n plus 1 for each I between 1 and rho, right? Such that t raised for rho minus 1 is less than n. We got this construction actually. Okay. Simple number theory. Again, discrete math to provide this nice distribution, right? Here, replication factor is 3. Okay. Then we thought of, I mean, Kannan Ramchandran used regular graph, right? I said I should generalize this idea. तो कुछ नोड्स की डिग्री सेम रहने दो, कुछ की बदल देते हैं. तो I called it weak regular graph. Okay. Means now we have flexibility. सारे पैकेट मतलब सारे नोड्स में सेम नंबर ऑफ पैकेट्स नहीं रहेंगे, कुछ में वेरी कर देते, किसी में 5 रखेंगे, किसी में 4 रखेंगे. एंड कैन आई डू द जॉब? आंसर इज यस, एंड दैट इज this. You see, our solution, this is a partial regular graph we call. Partial means, now you can see that what is the degree of u1? 7, right? u2 is 7. एक नोड की डिग्री अलग है किसकी? u9 की, right? So you can see that corresponding vector, packets are like this distribution. So here I am keeping a null packet. Number of packets are no different. So this is also a solution from graph. Now the question is, see, this is the contribution done by BTech student, people like you, right? What he has done. So I asked him, okay, this partial regular graph solution is fine, but can you give a construction so that a beautiful mathematical construction so that we can construct these partial regular graph? And that's what we worked out. I gave them hint. I don't do the job, I only give hint. And they have come up with a solution, and the solution is this. You see, this is the algorithm they come up with. Pick a circulant matrix. So matrix, circulant matrix means first row, you write some first row, second is just shift, third is another shift, fourth is another shift, and so on. Circulant matrix whose first row is like this, in a very specific polynomial. And then get a permutation matrix like this, and expand this matrix to make another matrix Sn like this, add another matrix C and D minus 1, this kind of matrix to get this PRG. So you get basically a matrix like this, which is the adjacency matrix of the graph. See? So this is the circular matrix. The first row is coming from that polynomial, and from there you do all these things. Final answer is this, and this can be converted into that packet distribution thing, the whole graph. The beautiful thing, algorithm given by people like you, right? You should have this ability rather than competitive programming. Okay. Another some other ring constructions we have given. It's like that we say that, okay, suppose we have theta packets and there are total n nodes. हम क्या करेंगे, एक सर्किल के ऊपर नोड्स को ड्रॉ करेंगे और इन सारे पैकेट्स को रेप्लिकेट कर लिया. Suppose we replicated these certain number of times and I'm just throwing packet on each node, and then it's an interesting thing actually. You see, this distribution This is another construction, basically, another algorithm for doing these things. All kind of solutions or replication packets. You see, this is how the ring construction works. So basically, I have on the circle, I have marked these nodes, and I'm just distributing packet 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Keep rotating until you are exhausted with all the packets. And this gives us that now that means packet 1 is common between U0 and U1. Node U0 and U1. Packet 2 is common between node U1 and U2. Packet 90 is common between node U0 and U1. So we know the common things. It's a very nice solution. Another solution. Common sense, right? And you get the answer. You don't require competitive programming for this again. Right? Anyway, so that's all about one application. How कितना time बाकी है अभी? हाँ? आधा घंटा अरे आराम से हो जाएगा अभी तो. So this was one application. Now let me okay, can you see this? Now we are going to talk about trees. सबसे simple topic है, very easy, right? What is tree? रोज देखते हो tree, right? So tree is basically a kind of, can think of a data structure also as well. By the way, so I'm asking with this is a tree? Tree does not have a loop kind of thing, right? So it doesn't have any loop, right? This is a tree. What about this? This is a tree, right? All these are graphs, right? What about this? This is not a tree, right? Because there is a loop here. You can say that from E, B, A, D, E, E, B, A, D, E. There is a loop here, right? So this is not a tree. The other graph is also G4 is tree? No. So broken. So idea is connected graph which doesn't have a loop is a tree. Simple idea, right? Okay, then there is the idea of rooted tree. ऐसा tree जिसका root हो, right? So we have, this is with root A, you can see this is a tree, this is another thing, with root C is a root, right? Okay. Now actually there are some common definitions that you use. If this is a tree starting from A is a root, so parent of, so you can see what does it mean by parent? Parent of E is what? E का parent क्या है? B is also, B is a parent, right? You can say that overall. And oh sorry, C here. Yeah. Yeah, sorry. Parent of C is B. Okay, fine. The children of G are Hij. Children of G are Hij, right? Which is clear. The ancestors of E are E, CBA. So ancestor of E are CBA. Okay. The descendants of B are, so descendant of B, I can see what are the descendants, right? You can always know. The internal vertices are, what are the internal vertices? A, B, C, G, H, J. बीच वाले, right? Leaves को छोड़ देंगे, right? Then leaves are D, E, F. So these are leaves, right? D, E, F, K, I, L, M. These are leaves, right? Subtree at G. So I can take some portion of tree from here out with G as a node. So this is a subtree. Common definition. ये सब पढ़ा हुआ है ना? इसीलिए मैं ऐसे ही चला रहा हूँ हवा में, नहीं? That's okay. By the way, I think you have, since you have done on beautiful projects, right? You must be knowing more than whatever we are teaching here now, right? After a project, you get some confidence, right? So anyway, so then binary tree. अगर खाली दो खत्म कैसे हो गया? ठीक है. So we have binary tree, right? So T1 is known as full binary tree because each of its internal vertices has two children, right? Then T2 is a full three-array tree, right? Each internal vertices has three children. T3 is a full five-array tree, right? T4 is not a full M-array tree for any M, as some have two children and some have three children, right? So, because the last one is having two children, for example, you can see, right? So these are examples. Then we can talk about left child, right child. Left child of D is F. This is left child, this is right child of D, right? Left subtree of C is HJ. Right subtree of C is that IKLM, right? ये सब बहुत ही स्ट्रेट फॉरवर्ड है ना. By the way, they are useful in chemistry, a lot of places actually. Chemistry is one very important thing. And I think some of you might be using Linux or Unix file system. There you can see this kind of file system tree, right? The structures inside, how the files are arranged, folders are arranged, right? Slash user, slash bin, slash tam. So slash user, slash bin, right? Slash user, slash spol, right? Those kind of things are there. Now there are some properties of tree. A tree with n vertices has n-1 edges. ये पढ़ा हुआ है ना इंडक्शन से, ये भी पढ़ा होगा, right? अगर tree में n vertices हैं, it will have. By the way, these trees are quite useful in number of applications. For example, in certain algorithms, you can design searching, or you can study complexity in sorting algorithms. Different places you can find applications of trees. So very important, simple idea, not very difficult, right? So, I mean, the proof involves induction. I think that is also okay. Suppose that every tree, true for base case, if n has one vertex, it will have zero edge. One vertex will have zero edge, right? Suppose every tree with k vertices has k-1 edges. Now we consider a tree capital T which has k+1 vertices. Then there will be a tree T prime which will have one vertex attached like this with one edge. Here we can assume using induction hypothesis that tree has, with k vertices has k+1 edges, right? So here since T has k vertices, so suppose T has k+1 vertices, one vertex is here, so T prime will have k vertices, so it will have k-1 edges. So k-1 edge plus one edge will give you k edges in the whole tree, right? Simple idea. Okay. Now I think I'm going to do just one last application, which is data compression. So normally you see that the first time people looked at English, so we know that there are certain structural properties of English. There is a famous paper by Piper. I think Piper is the name of the Hux and Piper, I guess, the name of the authors. They write a nice paper. They wrote a nice paper that studies the structural properties of English. Means if you look at any English text, the probability of occurring E is very high. E will occur. Then there are some other letters. So there is a table actually. So now, by the way, some of your seniors have done work with me. They have done the same thing for Sanskrit and Hindi. language. They have studied this. तो कौन सी मात्रा आती है, क्या आता है, कौन सी चीज कॉमन आती है, that they have done in this paper is we have to still submit it, but they have done this work. Course में किया, right? So from your course there should be paper. I don't know how many of you have written any paper here, but by now you should have it. So this property, statistical properties, can be exploited to create encoding of letters, right? Now the thing is that if we, if we take all this, say suppose there are 26 alphabets, right? A to Z. Now if I map it to some fixed binary strings, so A will assign suppose 5 bits, B is assigned 5 bits, C is assigned 5 bits. And then if you try to do this encoding, there will be an issue. Of course, it will take more data. So Huffman thought that we can utilize this statistical properties of English. Because E is occurring quite often, we can assign E the least number of bits. Okay. So you will use E only with 1 bit. Another letter which is occurring more often, we will use 2 bits and so on. Okay. And this bit assignment is done through a tree structure. So we call it tree encoding. Okay. So this will help you to understand how to design. I'll only do an example. No theorem, nothing. I mean, that is easy. Example will give you an understanding, right? So first of all, see the encoding here. This is known as prefix code. What is our prefix tree? So starting from, you can see that there is a top, there is a root node. On left side, there is, so when you move towards left, I will assign 0. If I move towards right, at the edge is 1. I will assign 1 on the edge, right? 0, 1, 0, 1. So E, A, T, N. So how do we read this? So what is the encoding for E? Because E is coming from root through only single 0. So E is assigned as 0. Right? Now look at A. So the first bit is 1 and then is 0. Then only you can come to A. So A encoding is 1, 0. What about T? 1, 1, 0. Right? The next one. N is 1, 1, 1, 0. And S is all 1. Right? This is a very simple prefix code, or the prefix tree, we call it, right? This kind of thing is used for encoding, right? So one thing to remember, whenever we move towards left, we assign 0 on the edge, and on the right we assign 1. Okay, this is the clear distinction, right? Then there is the algorithm. And so basically in that case, this is how you do the encoding, right? So now suppose you receive 1, 1, 1, 1, 1, all this, suppose this 1, 1, 1, 1, 1, 0, 1, 1, 1, 0, 0. So you take the first 4 is S, then A, you can go back actually, right? So first of all, how do we do this encoding? So now let me show you an example. So look at this A, B, C, D, E, F. There are these, how many? 1, 2, 3, 4, 5, 6. 6 alphabet letters are there. Each has certain frequency. How many times they occur? So A has 0.08, B is 0.10, C is 0.12, D is 0.15, E is 0.20, F is 0.35. Some frequency is there, right? Now, based on this, I have to make, our final goal is to construct that prefix tree so that I can do the encoding for each alphabet. Okay. And so the number of bits assigned to each letter will vary. And I want to minimize that actually, right? So what should we do? So first of all, initial forest, I write down all the things like A, B, C, D, E, F, assign the frequencies. Now what I do, I look at the lowest one. Lowest one is 0.08 and 0.10. So I combine these two nodes, okay, and make a tree. In the next step, you see that, so when we add 0.08 and 0.10, we get 0.18. Right? So node value is 0.18. Now 0.18 is bigger than 0.12 and 0.15. So the C and D will come ahead, and 0.18 goes to the third one with 2 child as B and A. Got it? And B side in left we assign 0 and right side we assign 1. Okay. So step 1, initial forest. So initial forest is step 0. Step 1, we have ordered them, and we have combined the 2 lowest values, sum them, form a tree, and do the reordering. So step 1 is this. Now what is left? Now you see the lowest one is 0.12 and 0.15, right? So we can add them. That will be 0.27. 0.27 we form a tree, But now 0.27 is bigger than 0.18 and 0.20. It goes at the third location, right? The first location is now 0.18 E in step 2. E is 0.20, and the third one is 0.27, and D and C on the other side. Remember, whenever we are whenever we are assigning, so on the left side we assign 0, right side we assign 1. Then there is a final F. Okay. So once we are done with this, then what is the lowest one? Again, now 0.18 with 0.20 we should combine. So we are combining this, and we are getting actually this. This, right? So 0.38 is there. One side E assigned on the left, and the other side you assign 1 in the overall tree, right? So like this, we keep on continuing. Finally, you will have something like this. Okay, a final tree. Now you can do the encoding. What is capital A here? 1, 1, 1, right? Assignment of A is 1, 1, 1. What is capital C? 0, 1, 1. 0, 1, 1, right? So we have all the things. A is 1, 1, 1, C is 0, 1, 1, E is 1, 0, capital B is 1, 1, 0, D is 0, 1, 0, and F is 0, 0, 0. So one can compute average number of bits to encode a symbol using this mechanism. Because A occurs 0.08 times, the length for A is 3 bits. 3 into 0.08 plus 3 into 0.10, you can compute the value is 2.45 bits only. Average, right? So quite, yes. Huh? Table nahi, I don't have a table here, but I would have shown to you. Hux paper ke table mein dikha do. So they, in that table, the frequency is different for each one, right? There's no same frequency here, right? Anyway, so I think this is the whole idea about Huffman coding. This binary Huffman coding has been generalized to ternary, quaternary, and in our DNA storage paper, we have used, ternary Huffman coding or DNA data storage. So all kind of things, when we want to compress the data, people use Huffman coding. It's quite easy, right? So, और कोई question? I think we are done with the whole course. If you have any question, कोर्स तो खत्म हो गया, कोर्स में कुछ बचा नहीं है. अगर कुछ बोलो तो एप्लीकेशंस के हम और बात कर सकते हैं. यू वांट टू लर्न या कॉम्पिटिटिव कोडिंग सिखाऊं? हाँ, जो कोर्स डिजाइन किया था वो ऑलमोस्ट खत्म हो गया, ट्री तक ही था, एंड दिस इज द लास्ट थिंग एक्चुअली, राइट? और वैसे तो शास्त्र अनंत है, विद्या का पारावार नहीं है. ऐसे में मनुष्य को सदैव मूल तत्व पर विचार करना चाहिए, राइट? मूल तत्व तो हो गए. हाँ? तो एसीबी पे होगा ना, 4 होते हैं, 4 होते हैं एसीबी. मेरी इसमें मैपिंग करनी पड़ती है. नहीं नहीं नहीं. सो एनी क्वेश्चंस? मैंने सोचा लास्ट लेक्चर तो ले ही लूं कि बोलो मैंने ही कंप्लीट किया कोर्स, राइट? एटलीस्ट क्रेडिट शुड गोज टू मी. So I think I hope you enjoyed the course basically, right? If you have any doubt, anything, you can send me a message. You have the number, right? Interact with me. If you want to start a company, interact with me, right? And I think some of you, I think I'm still telling you, competitive programming is not going to take you further. Only if you have certain skills. Try to learn as many skills as possible, right? So for example, prompt engineering is very important thing. I think I told to some of you, right? You should do some of these courses, learn some new skills and try to build. At least maybe अभी तो समर चला गया, ज़्यादा नहीं है, शायद दिसंबर में at least you should be able to write 30,000 40,000 lines of code. ऐसा कुछ प्रोग्रामिंग करोगे तो कॉम्पिटिटिव प्रोग्रामिंग की जिंदगी में कभी जरूरत नहीं पड़ेगी, राइट? राइट. सो आई थिंक दैट्स ऑल. वैसे मैंने प्रसन्नजीत को बोला था, if you want to learn more about complex networks, he can take some lectures on that if it is there. We will tell you if there is I will ask him, right? Some more applications like complex networks are very useful because these days complex networks has been applied for computational food. How to make algorithms which can generate food, new algorithms for food making. So computational food can be done using complex network, right? It's a beautiful area. So is what is known as power law. I think since I have not taught to you about graph theory, basically there are a lot of interesting networks. For example, there is a collaboration network. If you write a paper with someone else, like Paul Lados network is there. Paul Lados at number 0. Paul Lados has written a paper with someone that will get number 1, Lados number 1. Another person writes with Lados